Jest dobrze. I tu włóż. Kliknij. Bardzo kliknąłem. Dobra, idzie. Ja jeszcze sprawdzę.
A coś tu przerzucam. Nagrywamy kamery, coś?
Tu po kolei. Tak, jest się, tak.
A coś, włączamy tam kamerę?
Ona jest
Do
włączona.
jakiejś, chyba tam do jakiegoś trybu takiego oszczędzania energii przechodzimy.
Przechodzimy.
Nie.
Nie, działa
Tak?
bardzo.
No
Nie się przyjrzycie wszyscy. Poszło.
Znaczy to cały czas się transmituje.
It's my great pleasure to announce a lecture to be presented by Professor Sławomir Kołodziej from Jagiellonian University in Kraków. The title of the presentation is, as you can see, Solutions of Complex Hessian Type Equations.
Thank you for the introduction, and let me first thank the organizers for the invitation and the possibility to speak here. It's a wonderful meeting, so and everything goes smoothly. So my topic are complex Hessian equations, highly nonlinear PDEs. But I will start with something. With something elementary, which means, yeah. Oh, no. Okay, we go back. So we start with something elementary, which are elementary symmetric polynomials. So we have a formula for Sm lambda. Lambda is n vector from n-dimensional space. And elementary symmetric polynomials are one of the examples of so-called hyperbolic polynomials studied first by Gordon in late 50s. You have a definition here. A polynomial is hyperbolic with respect to point vector A if for any line in the direction of the vector A, the polynomial has exactly k real roots. Then it is called the polynomial of degree k. One thing which was proven in Gordon's paper is that the cone defined here as gamma m is a convex cone. So it is defined by n inequalities as j lambda bigger than 0, j between 1 and n. So for instance, gamma 1 would be a hyperspace given by sum of lambda j's bigger than 0, and the top gamma n is the positive octant where all lambdas are positive. Gordon also proved that the function Sm to the power 1 over n is concave on this cone gamma m. And there, now I will present several identities or inequalities for these dot-symmetric polynomials, which are later applied in the proofs of theorems. I will not give proofs, but one should be aware that such things are used there. So first we have this definition of SKI. So you take the symmetric polynomial of degree k, and you replace all lambda i's in this formula by 0, and then you get SKI. And as I said, there are inequalities. So classical Newton-Maclaurin inequality says that this expression Sj over polynomial n over j to to the power 1 over j is decreasing in j. And we have another inequality which is quite often used in nonlinear PDEs. So again, we take this Sm minus 1I, where lambda i's are replaced by zeros, and we replace those lambda i's by mu i's, and we have this sort of concavity inequality. There are more special results. For instance, Iwoczkina gave characterization of the cone gamma m, from which in particular you get that at least m lambda n lambda j's must be positive. And also inequality which is used in the results which follow is by Lin and Trudinger. We compare SMI with SM at lambda, and there is a universal positive constant. It's not written here, theta is of course positive. There is such a universal constant for which we have this bound. And now we come to equations. So by a small abuse of notation now, instead of Sm lambda, I write Sm of A, where A is n by n Hermitian matrix. And we take lambda j's, the eigenvalues of this matrix. And then the equation we consider is the following. We take Sm acting on the Hessian matrix, complex Hessian matrix of a smooth function u. And we prescribe the right-hand side of the equation. Here it is denoted by f. So we look, we prescribe f, and we look for the function u satisfying this equation. And the equation is called M-Hessian equation. You can write it in terms of differential forms. I use the notation that, well, we split the operator d into d and d bar, where d bar denotes that we differentiate with respect to anti-holomorphic variables, and we also often use this operator dc. You don't need to remember what is dc, but what is important is that, maybe I write it here. So ddc is the same as numerical constant times delta and delta bar. Okay, so in this differential forms notation, we have the equation in the last line, where beta is the Euclidean 1-1 form in Cn. So beta to the power n is just a volume form. And this equation is elliptic if we restrict ourselves to functions with eigenvalues in the closure of the cone gamma n defined on the first slide. And those eigenvalues belong to the cone if we have m inequalities written in the last line at the moment. So for k between 1 and m. So for instance, if m is equal to n, we get the Monge-Ampère equation, because this is ddc u to the power n equal something. Some background: the real Hessian equations were studied earlier, at least since 80s. First important papers by Caffarelli, Nuremberg, and Sprach. They proved that the Dirichlet problem for this equation is solvable for smooth and positive data. Iwochkina, she proved some a priori estimates, and Schrödinger-Wang considered weak solutions of the equation. Then, on the right-hand side of the equation, we don't have a function times the volume form, but some given non-negative measure. Now, if we pass back to the complex case, know that for k equal 1, we just have the Poisson equation. And as I said, for m equal n, we get Monge-Ampère equation, which was studied much earlier. The Monge-Ampère equation is kind of special here because then all eigenvalues are positive, which is not the case for lower n's. And then working, for instance, with a priori estimates, it's much easier for the Monge-Ampère equation than the general case. And just the idea, so if you start to study these complex Hessian equations, you have a choice. You can try to imitate the methods which work for real Hessian equations, but then if you want to work with weak solutions, then you can try to use the methods which are known for the for complex Monge-Ampère equations. And this was first done by Błotsky in 05. But before Błotsky, the Dirichlet problem for smooth and positive data was solved by first Nyakua in 86 and then S.Y. This is kind of strange because this first paper was forgotten for a long time. So nobody, Nyakua, I think he was a PhD student of Nuremberg. He wrote this, he solved the problem in his thesis, and maybe he left mathematics later because there is no sign of his activity later on. But anyway, so we take a smoothly bounded domain in Cn, which is so-called n-1 pseudo-convex, which by definition means that the Levy form at each point of the boundary has eigenvalues in this gamma m-1. If you want, you just can think of convex domains. So the convex domains are just special case, but it doesn't matter. Then we impose some boundary data, which should be smooth, and we solve the M-Hessian equation, obtaining, in this case, smooth solutions. So if the data is, if f and phi are smooth, then the solution is also smooth. And as I mentioned, Błotsky considered weak solutions of the Hessian equation, but then we have to, maybe I go back first. Yeah, so here at the top we defined M subharmonic functions. So M subharmonic functions are those with the Hessian matrix having eigenvalues in the cone gamma m. But this definition is correct for functions which are of class C2. And now we drop this assumption. We do not have any smoothness. So we consider subharmonic functions, and so this is a two-step definition. Okay, so first we take alphas, which are n positive, and which by definition means that we have a collection of inequalities here. And then, considering all such collections of alpha j's which are n positive, we wedge EDCU with such guys, and we should get something which is non-negative. So this is the definition for M subharmonic function which is not necessarily smooth. And in his paper, Włodzki in particular posed a conjecture, which is still open in general, about integrability of M subharmonic functions. So they should belong to LQ for any Q smaller than M times N over N minus M. And this would be an optimal bound for Q, since if we take this G here, which is the fundamental solution of M Hessian equation, then it belongs to LQ if and only if Q is smaller than M times N over N minus M. We were able with Sławomir to confirm this conjecture under extra hypothesis that our function is bounded near the boundary. So if the singularities are isolated, then this is true. And this was useful to get weak solutions of M Hessian equations. So we obtained the following theorem. Omega is as in the previous one. The right-hand side of the equation is in LQ for Q bigger than N over N. The boundary data continues, and then we can find continuous function U, solving the equation for F with the given boundary data. And this bound for the exponent Q is optimal. It cannot be smaller than N over N. Later, there were improvements of this statement. For instance, if the boundary data is nice enough, then the solution is in fact Hölder continuous. As I said, except for this confirmation of Włodzki conjecture, the rest goes more or less the same way as for the Monge-Ampère equation, complex Monge-Ampère equation. And there were further improvements. For instance, in the case of complex Monge-Ampère equation, Segrel introduced so-called finite energy classes. In those classes, you have plurals of harmonic functions which are not necessarily bounded, for which you still can define the Monge-Ampère operator. And then you get very general statements, like, for instance, if you take a measure which is non-negative, which vanishes on pluripolar sets, then you can find the solution of the Monge-Ampère equation in such a finite energy class. And this singular result was then generalized by Chin-Bloom to cover complex Hessian equations. And there are also theorems saying that if you have a subsolution in some class of functions, for instance, bounded or Hölder continuous functions, then you can find solution in this class. So if you have bounded subsolution, then you have bounded solution. If you have Hölder continuous subsolution, then you have Hölder continuous solution. But in between, you could consider continuous, and then we don't know even in the Monge-Ampère case. So even in the Monge-Ampère case, we don't know if continuous subsolution implies continuous solution. So, as I said, we can use either this real Hessian equations method, and for smooth solutions they work, or we can adapt pluripotential theory, which works for complex Monge-Ampère equation, and then those methods also work up to a point. However, there is quite a big difference between plurals of harmonic functions in the complex case and these M subharmonic functions. They are much less understood than plurals of harmonic functions. For instance, if you, just by definition, a plurals of harmonic function is a function which is subharmonic on any complex line. And here, in the last sentence, you see that we know that the M subharmonic function is subharmonic on n minus m plus 1 affine subspaces, but this is not if and only if condition. And now we pass to compact Keller manifolds. So the equation changes. It has to change because purely subharmonic functions or subharmonic functions on a compact complex manifold are by necessity constants only because of the maximum principle. So the equation, in the equation now we have this omega plus ddcu instead of ddcu to some power. Here omega is a Keller form on this compact manifold X. F is again the given function. It has to be normalized by this condition on the right hand side because of the Stokes theorem. So this is a necessary condition to have a solution. And then we look for functions which are called M omega subharmonic, which this condition means that we have inequalities in the last line. And again, on this space of functions, the equation is elliptic. In case of n equal n, again, we obtain the Monge-Ampère equation, which is related to Calabi conjecture, which was proven by Yau. And again, you can try to use Yau method of proof to get solutions for M Hessian equations in this case. And this works up to a point. So if you assume non-negative bisectional curvature, which is very restrictive assumption, then you can really use Yau estimates and get the solution. But in general, the C2 estimates are missing. And they had to be replaced, and they were replaced by Hu, Ma, and Wu, who adapted the method which was used before by Zhou and Wang for real Hessian equations on Riemannian manifolds. But this is not it's not a direct adaptation. The proof is like 10 pages of estimates to adapt to the complex case. So with this method, you can reduce C2 estimates to C1 estimates. So here in this inequality on the left-hand side, so what we have here are second order derivatives bounded in some norm, it doesn't matter. So second derivatives are bounded by first derivatives squared. Which means that if you can prove the estimates for the gradient, C1 estimates, then you get C2 estimates. In Yau's case, he directly obtained C2 estimates. He didn't need C1. Kumau also suggested that you can use so-called blowing up analysis. I will try to explain on the board what does it mean. Maybe suppose we do not have C1 estimates, which means that there exists a sequence of functions on the right-hand side, fj's, and corresponding solutions, say uj's, so that the gradient of uj in some norm goes to infinity. What you can do in this case, well, first of all, passing to a subsequence, you can find a point in your manifold, call it 0, such that the points where this maximum of the gradient is attained, those points converge to this. We pass to the subsequence. Okay. And we are in some chart. And then what we do, we dilate this chart in such a way that in new coordinates, say we have now uj's in tilde in new coordinates, now those gradients have norm 1 all the time for every j. So we do it for every j, then the chart blows up to Cn, and in the limit, you have to prove that the limit exists. In the limit, you get a function, say u tilde, which is non-constant because the gradient at 0 is now 1, which is bounded with bounded gradient because this is the maximal gradient for this function. And you can prove that in the limit, you obtain homogeneous M-Hessian equation. Homogeneous meaning that on the right-hand side you have 0. And we call such solutions we call maximal. They correspond to harmonic solutions for the Poisson equation. With DNF we are able to prove that such functions do not exist. That we have a Liouville type theorem for M subharmonic functions. So if M subharmonic function is maximal, meaning that it solves the homogeneous equation, is bounded and has bounded gradient, then it has to be constant. So this way we obtained C1 estimates, and combined with Huma and Wu, we could prove the analog of Calabi-Yau theorem in case of M-Hessian equation. Still on Keller manifolds, you can consider weak solutions, and as in the case of domains in Cn, if the right-hand side is in NP, P bigger than n over m, then one can obtain continuous solutions. Again, this bound on P is sharp. If you assume, moreover, that non-negative holomorphic bisectional curvature is holomorphic bisectional curvature is non-negative, then the solutions are further continuous. And those results from the previous slide, so Huma, Wu, and Diner and myself, they are quite robust because in all theorems which will follow now, which are twisted version of Hessian equations, those methods still work. They have to be adapted in each case, but more or less the same procedure works. And very recently, just last year, Guo, Fong, and Tong gave a different proof of existence of, well, this Calabi-Yau type theorem, and in particular, infinity estimates or C0 estimates in this case. And now we pass to something more general. So instead of Keller manifolds, we consider just Hermitian compact complex manifolds with Hermitian metric omega, which means that omega is still a positive form, but not necessarily closed. And then there is a change because we cannot find a normalization for F which gives the existence of solutions. We have to look for solutions U and constants C so that this equation holds. We do not know a priori the constant C. Yeah, this is because we don't have our form is not closed. There are some other technical obstacles in the theory. Well, one should realize that on any compact complex manifold, you can find such a Hermitian metric. It's not necessarily the case for Keller manifolds. I mean, there are compact complex manifolds for which no Keller metric exists. In this case, in this Hermitian case, for the Monch-Ampère equation, the first results were obtained by Tosatiu and Weinkoff. In fact, some special case was done earlier by Chevier. And for general M Hessian equations, Zhang and Sekele-Higgi independently proved the existence of solutions for smooth and non-degenerate data. And so they adopted the method from the previous slides, but also had to do some extra work. So Zhang, he had to prove some new inequalities for symmetric polynomials, and Sekele-Higgi extended the method of Guan of so-called subsolutions. I will not go into this because it's a bit technical. And now again we change the setting. We have a Hermitian manifold as before, but now we have a manifold with boundary. So we have big Hermitian manifold, and within this we take open sets with small boundary and with some possibly convexity of the boundary. And the equation is also more general, because now we have two forms, alpha and omega. So this alpha is not necessarily positive, but this is 1-1 form, the real 1-1 form, in this cone gamma m, and omega is our Hermitian form. And we need to solve this equation. Again, first for smooth data. And it was first done by Collis and Picard. For smooth data, they proved that if a subsolution exists for this equation, then there exists a solution. And in the recent paper with Nguyen, we developed the theory with which we can treat weak solutions. In particular, we define this M Hessian operator for functions which are just bounded. And we could extend the result of Collins and Picard, saying that if you have a bounded subsolution, then you have a bounded solution. A related result, also very fresh, is by Wu. It is related to so-called Wess-Zumino-Witten type equation for harmonic maps into the space of color potentials. So we have a map, maybe right. Say we have X omega compact Keller. Keller potentials in the given cohomology class are the functions U which satisfy this condition. And then you consider a map from omega to the space of those potentials, call it H omega. Such a map is called harmonic if it is a critical point of some energy functional. And Donaldson wrote down the equation which produces those harmonic maps. And this is the equation we have in the middle of the slide. So this is number, and Wu obtained solutions in a very special case, but for the homogeneous equation. So on the right hand side we have 0. And now the equations I discussed can be still generalized to something more general. So first of all, we can generalize the operator, then the background for omega in this case, and also we can admit on the right hand side dependence on the gradient of the function and so on. So typical generalization is like this. We take a cone gamma, which is between this gamma n, which is the smallest of gamma j's, and gamma 1. And we consider equation f of lambda equal g. With some conditions imposed on f, f should be symmetric, should be homogeneous in lambda, meaning that if we multiply lambda by t, then f of t lambda should be like t to some power times f of lambda. It should be increasing in lambda, each lambda j on this gamma, and sometimes they need some other conditions. And here lambdas are not necessarily eigenvalues of the Hermitian form, but for instance, if omega has coefficients gjk and omega plus bdcu has coefficients, say, gamma g tilde jk, then you take the matrix, the inverse of the first one, composed with this one. Then this function, this matrix has some eigenvalues, and those eigenvalues are our lambdas here. And some examples and applications in geometry. First is J equation. Here, chi is a given fixed form on a Keller manifold, and we look for another Keller form, omega, satisfying the equation omega to the power n equal omega to the power n minus 1 wedged with chi. In terms of those symmetric polynomials, this is just Sn minus 1 over Sn of lambda equal to a constant. And this equation was introduced by Donaldson in the framework of some moment maps of Lie algebra of diffeomorphisms of symplectic manifold. There is a corresponding parabolic equation or flow, J flow. And by this parabolic method, Songen-Weinkoff solved this J equation first for smooth data. There are more general Hessian equations. So here you see on the left and on the right we have different M Hessian operators. This type of equations were solved recently by Sekele, Hibi, and Sun in a more general version. There are peak non-jumper equations introduced by Harvey and Lawson, defined here. So this lambda I is the sum of lambda I j's for some collection of ij's of length p. So Harvey and Lawson introduced the equation, but it was solved by, again recently, by Guo and Tong. One can, as I said before, one can also generalize the background metric. Instead of having something positive, you can consider something semi-positive, which, for instance, in geometry appears when you have a, say, Keller-Ritchie flow. In the limit, if this limit exists, the Keller metric degenerates, and you get something which is only semi-positive, for instance, net, as here on the slide. And then you would like to have a priori estimates which are valid up to this limit. So we consider the family of metrics, and we should have the same estimates with the same constants for the whole family of metrics. So this is also something which is being done nowadays. And shortly, some geometric applications. So some time ago, Fu and Yao wanted to solve a Hall-Strominger system, which appears in supersymmetry in string theory. And with some additional ansatz, they reduced this Hall-Strominger system to the Monge-Ampère type equation, but only in dimension 2. And then the solutions which are obtained from this Monge-Ampère equation corresponds to some toric vibration over K-free surface. And then if you want to generalize this to higher dimensions, higher than 2, then the equation you obtain is Hessian type equation, which we have here. And this is far more complicated than the one discussed before, sorry. Because, well, first, the sky is given, but it also depends, it does not only depend on Z from the manifold, but also on the solution U. So this is more general, but also the right-hand side is more general because, again, this given function psi also depends on U and the gradient of U. Especially this gradient term was quite terrible in estimates, but after several years, those people from Picard and Zhang were able to solve the equations under rather mild assumptions. And the Chinese guys from Peking University also obtained a slightly different proof. Another application, so-called Goduchon metrics. Again, as I said, Keller metric that does not necessarily exist at a given manifold, compact manifold. But by Goduchon theorem, Goduchon metric, which satisfies this equation from the first line, such metrics always exist. And there is an analog of Calabi conjecture, which is Goduchon conjecture, saying that given Cherno-Ricci curvature form, you can find a Goduchon metric which has this Cherno-Ricci form as its curvature, or maybe a simpler expression is that you can find Goduchon metric with prescribed volume form. And quite recently, Sekelehi, Itosati, and Wanikov confirmed this conjecture, and they had to solve this so-called coupled equations. So you look for alpha satisfying the equation in the last line. So we want to find alpha such that this equation holds for given f and b. P is not given, b is some constant. So you look also for the constant. And this alpha to n-1 is given by this rather complicated expression with the function u, which is unknown. So we first find u satisfying the equation, and then this alpha n satisfies this. And maybe the last application. Now we go back to real variables. This is rather classical that you have, if you have a smooth function u on Rn, then you can consider the so-called gradient graph given by x and the gradient of u at the point x. And this graph is called special Lagrangian if it minimizes area among all submanifolds with the same boundary. And Harvey and Lawson proved that such a gradient graph is area minimizing if the following equation holds for eigenvalues of the Hessian of U. So now we do not have symmetric polynomials of lambda j's, but we have some symmetric function of lambda j's. The right-hand side is a constant. And there is a corresponding equation which appears in supersymmetry again. It was considered first by Collins, Jacob, and Yao. So in this equation we have the same volume form omega plus I chi, where chi is a real closed smooth form. Omega is a given Keller form. And here we have imaginary part, which should be equal to constant times the real part of the same form. And in terms of eigenvalues of some matrix, it corresponds to this equation. And then the solutions of this equation via some Fourier Mukai transform correspond to special Lagrangian surfaces in the mirror manifold of the given manifold. Okay, that's it. Thank you. And as the last speaker, I have the privilege to thank the organizers for this fantastic meeting. I think everyone has the same opinion. Okay, thank you.
Thank you for the interesting lecture. It's time for questions, remarks, comments.
I have a question. What about uniqueness for all those equations you were talking about?
Usually it is, but in the Hermitian case, you may have problems. Yeah. So if you have this, for instance, Hermitian manifold with boundary, then in general, I think uniqueness is not yet proven. Yes. In the Keller case and in Euclidean case, it's uniqueness is true, but in the Hermitian case, not necessarily.
What about quotient Hessian equation?
Again, on Hermitian manifolds, you may have problems.
Another question?
Thank you for your talk. I have a quick question. The K-Hessian equations, one of the applications is the prescribed curvature problem to find hypersurfaces. Is there such an application in the set of complex K-Hessian equations to find certain hypersurfaces in some complex manifold, something like that?
Could be. Yes, because, well, you have this curvatures between Gauss and mean curvature, right? And the Hessian equations in the real case correspond to those in between, right? But no, I do not recall any papers considering exactly this. It's rather very fresh idea, so maybe they will appear quickly. It depends how important those intermediate curvatures are in the complex case. Hard to say.
Another question or comment? If not, then let's think once more to speak.
Okay, we are preparing closing. Don't be afraid, the closing will be. We have the board of trustee of our meeting now slightly modified. Dean of the Faculty of Mathematics of the Łódź University of Łódź, Katarzyna Korbaczewska. Vice President of the Societat Catalana de Mathematics, Jean Botti. And President of the Polish Mathematical Society, Jacek Mikisz. We agreed that now it will be less formal, and then the formal speeches of the officials will be. So it was a great pleasure to see you all at our meeting during this fantastic week, and very good weather, which is not typical in Poland this time. I hope that you have much fun from time to time. Some work during this conference. I want to thank you, the members of program committee who prepared our general part of the meeting. I thank plenary lectures, organizers of the section, thematic sections, and the lecturers in the sections, and the number of lectures only in the sections was over 200. I think that the number is really good. So I want to thank to all of my collaborators who prepared this meeting. I start with the young people who help us. There was students of Technical University of Łódź, Patryk Nitkowski, Gabrysia Smejda, Stefan Nosek, Krzysiek Caban, Mateusz Lichman, Michał Pawlikowski i Filip Tudoboś. Students from the University of Łódź. Marta Budek, Asia Karasińska, Weronika Kusiak, and the persons who were visible here, our technical support, Czarek Świderski, and not so visible, but very helpful Tomek Marczak. Our office containing Marzena, Marta, Natasha, Olaf, and Antek, and the organizing committee. I mentioned some specializations in this committee. Małgosia Telepeta was responsible for hotels. Zosia Walczak and Jacek Rogowski for excursions. Kamil Niedziałomski and Żywilla Fechner for sport. Żywilla also for organizing Zatoka Sportu. Adrian Łydka helped us with some financing problems, some proposals, and Ania Lolanty, Szymon Głąb, Andrzej Komisarski i Darek Wardowski prepared some elements of logistics, program, help to organize session and other. And the specialization of Mateusz Krukowski and Viola Lipińska was this book of abstract. They simply prepared this book of abstract. Magda Górajska and Ola Orpel were responsible for eating. And I think everybody knows that this was okay. Grażyna Chorbaczewska and Żywilla Fechner organized all the events, especially this event in Zatoka Sportu, banquet. Grażyna organized concert. And finally, Marek Majewski and Filip Strobin were responsible for everything other which went well.
For bad,
my deputies in that, and remember that the only responsibility of this facts which went wrong is mine. I suggest to look for a moment for this person. So let me go closer. Obviously, some of the persons were exhausted. For example, the members of office are so exhausted.
Thank you.
I think we cannot forget about the person who was responsible for everything. I really don't know the thing for which he was specialized, because it was mentioned that we were specialized in something, but there was a person who was specialized really in everything. It was magic. And so, big applause for that.
Thank you very much. And now is the time for the official underline and closing. I suggest to start with our.
Okay, so there is one factor without whom this conference wouldn't be possible. I think it's always with each conference, so there are participants. So really great thanks for all of you, this present at the moment, and this who left this conference area. So please make a big noise for you and for the others. And I hope we started here some fruitful cooperation, so maybe we can meet somewhere else, not here, not during the conference, but reading our papers, reading about our results in the future, and maybe also in Łódź in some circumstances. So you are invited once again.
So, okay, in name of the Catalan Mathematical Society, I just want to express my gratitude to the organizers and to everybody who including all of us, that participated. I think this was really very nice. Well, everybody thinks that. And I hope that the collaboration, to strengthen the collaboration of that. So I have nothing else to add, just my gratitude. Thank you very much.
I would like to thank our friends and colleagues from Real Sociedad de Matemática Española, Sociedad Española de Matemática Aplicada y Sociedad Catalana de Matemáticas. Thank you for accepting our invitation for co-organization of this meeting and the patience when we postpone many times this meeting. I would like to thank all speakers for increasing our knowledge in various domains of mathematics, and it wouldn't be, of course, possible with the great work of the organizing committee, and we had already the persons here, and only thank the chairman of the organizing committee now, Maciej Czarnecki, for making these things, this event possible here. And of course, I would like to thank you, the University of Łódź, for hosting us here, and also the Łódź Technical University. So everything which is good should come to the conclusion, but it means that this is not the end, it is the beginning of something new, some new collaborations. So we would like all together to officially close our joint meeting. So we declare it closed. Okay.
Yes. I think it's, I mean, to be honest.
Yeah, I don't know whether it was a constitution.